Nuclear stellar clusters and supermassive black holes. Hello, I'm Melvyn Davies and this is work with Abbas, Askar and Ross Church at London University. So one way to build up a nuclear stellar cluster in the centre of a galaxy is shown here. What's happening is stellar clusters form close to the middle, are spiralling in and merging around the supermassive black hole that already exists there, shown as the red dot. What we want to consider here, though, is the question which comes first, the supermassive black hole or the nuclear stellar cluster? Can a supermassive black hole actually form after the nuclear stellar cluster is formed? There's good evidence that this might be the case in some cases because some galaxies, such as M33 shown here, contain no supermassive black hole, despite the fact that a nuclear stellar cluster is observed in this galaxy. And as shown on the right, there are a number of galaxies showing this property, with nuclear stellar clusters have low velocity dispersions, suggesting that the massive black hole is not so massive, even if it exists at all. So what we did then is simulated the merger of stellar clusters. So we model a number of stellar clusters and have them spiral and merge. In some clusters they only contain stars, whilst in others they contain what I call an intermediate mass black hole, where intermediate means here something between a few hundred and 1,000 solar masses. But crucially, we begin without a supermassive black hole. So the idea then is you take clusters shown here, some with black holes in, intermediate mass black holes shown as the black dots, some without. You merge them to form a nuclear stellar cluster, and later on we'll see we can also add gas to enhance the growth of the black holes. So key idea number 2 then is that intermediate mass black holes, so black holes of a mass of a few hundred solar masses, can form at least by runaway mergers in some dense clusters. So here's an example of calculations done by Abbas on this, where you look at the intermediate mass black hole mass formed in a set of number of clusters, each with 100,000 stars. So in about 10% of cases, perhaps up to a few tens of percent, we can actually form an intermediate mass black hole by runaway collisions or by the tidal disruption of stars to grow a stellar mass black hole to masses of around a few hundred to 1,000 solar masses. Key idea number 3 then is that 1 plus 1 equals 0. So what we're talking about here is the idea that if I have two intermediate mass black holes formed in stellar clusters that then merge to form my nuclear stellar cluster, so some of the stellar clusters coming in contain black holes, and so if two of them contain black holes, then what can happen is I end up with a black hole binary. Each black hole then is intermediate mass inside my nuclear stellar cluster. But what can then happen is that the black hole binary will spiral together by the emission of gravitational waves and merge. But crucially here is that when I get two black holes merging this way, I can eject them from a cluster because of what is known as the recoil kick, because of the asymmetric emission of gravitational radiation and thus momentum in the final in-spiral. These plots just show the results of our simulations. The crucial point here is the intermediate mass black holes' masses are much less than the mass of the cluster, so they don't affect the stellar cluster merger. But because they're much more massive than the stars, they sink very easily to the middle of the merged cluster and form a binary. And what we show in the plot on the left then are examples from runs where we see we make extremely tight binaries, separations only of a few AU ultimately, and they have merger times by gravitational radiation which are usefully short. And on the bottom right then is a calculation of the kick speeds we get, and you can see that the mass ratio is very important here. So unless the mass ratio is less than about 0.1 or 0.15, the recoil kicks received when the two black holes merge are in excess of many hundreds of kilometers a second, certainly sufficient to eject them from the nuclear stellar cluster. Key idea number 4 is that 1 plus small is larger. So if I have two black holes in a binary and they merge, if the mass ratio is less than about 0.15, then the black hole merger product can be kept in the nuclear stellar cluster because the kick is low, as we've just seen. So here's some simulations we've done then. This is the second piece of work we've done on this. This is work in preparation. And what we've done here then is calculate the seeds produced. So we look at the nuclear stellar clusters and build them up from smaller stellar clusters, from a power law distribution of stellar clusters matching the observed ones. And in a random way, based on the simulations Abbas has done, we populate some of the nuclear stellar clusters with intermediate mass black holes and some don't have them. And then we merge. And what we see here then, it's a complicated plot, is actually two things. There's observations of the red dots and the blue dots. And so we see that in a lot of cases, for example, the blue dots, a lot of them are downward pointing arrows because we see measured nuclear stellar cluster masses, typically of a few million solar masses, but only upper limits for the black holes, supermassive black holes. With the red dots, there's a more complicated mix, then some are upper limits for the black hole mass, and some are in fact at upper limits for the nuclear stellar cluster mass. Some of the most massive black holes are in massive galaxies which appear not to have nuclear stellar clusters. Okay, anyways, looking at the simulations though, what we have there is actually the number of IMBHs populated in our nuclear stellar cluster. So we have then blue dots at the bottom is where we have no intermediate mass black hole at all. The orange dots are where we have one, the purpley dots are where we have two, and the yellow dots are where we have three or more. Two or more, sorry. Three or more, sorry. And what we can see then is that the more massive the nuclear stellar cluster is, the better the chance that we have IMBHs at all and have more of them. So for lots of the low mass nuclear stellar clusters, say masses less than 1 million, it's really very likely that we have no IMBH at all, because we built it up from a small number of clusters, and it's quite possible then none of them had an IMBH in the first place. For the more massive nuclear stellar clusters, we have more IMBHs. So the idea then is that we can do two things with these seed IMBHs to make a Milky Way, as we see today. So we see the Milky Way on this plot here has a nuclear stellar cluster mass of about 10 to the 7 and a black hole mass of a few million. So clearly the seed masses are much less massive, about 10 to the 4. But what we can do is actually can build a nuclear stellar cluster with an IMBH, but then grow it later by gas accretion to make the IMBH, the supermassive black hole we see today. And that's shown in this plot here. We've allowed for accretion rate over 4 billion years, which is a reasonable time of active galaxies in the past, allowing at 10% of the maximum Eddington rate. And we see we get here then a range of black hole masses which easily accommodate the Milky Way shown at a few million solar mass black hole. So gas accretion at 10% Eddington for 4 billion years can easily match the observed black holes we see in galaxies today. We note also again in this plot that the low mass nuclear stellar clusters, the masses around 10 to the 6, often have the blue dots here. Again, those are the ones where the nuclear stellar cluster contain no IMBH and therefore it is not grown by accretion. So the idea then with M33, the galaxy without a supermassive black hole, is we make a nuclear stellar cluster without an IMBH, and then we simply have no gas accretion onto it because there's no black hole to grow, or even if we do have an IMBH, we have a very dry system with very low accretion rates. Let me summarize then. So we looked at 6 key ideas. We asked whether the supermassive black holes could form after the nuclear stellar clusters. We then had the nuclear stellar cluster built from the merger of stellar clusters coming in. Some of those clusters contained intermediate mass black holes. We had the point that if we had 2 intermediate mass black holes in our merger product, then when they merge, they could eject them. 1 plus 1 is 0. The recoil kit could remove them unless the mass ratio is less than 0.15. If the mass ratio is low, we can keep the black hole, and it can grow to a supermassive black hole by gas accretion and tidally shredding of stars. We think that in the Milky Way, the nuclear stellar cluster was formed with at least one IMBH, and that grew by gas accretion. And with M33, the galaxy close to us that does not have a supermassive black hole today, but a nuclear stellar cluster, we think that then it formed a nuclear stellar cluster probably without an IMBH at all. And if it had an IMBH, it has not grown because the system is dry. Very little gas accretion has happened in that system. Thank you for your attention, and please let me know if you have any questions.